Good. Right. Welcome to the lecture of material science. Today we are going to again talk about chapter 2. And before we move to the new information and the materials, let's have a quick recall about what we have learned on last week. This is a very important model called Bohr atomic model. And so there are 6 postulates for the atomic model. So, and we know that this is only one electron model. So no matter how many proton and neutron in the nucleus, you only allow only one electrons in the model, so that you can get equations according to this model. Okay, and also this is the simplest model to develop, to start to develop atomic model. And later on, we will introduce more complicated models for you. So the Bohr atomic model is a one electron model. So according to energy balance, force equal to 0, and the quantization of angular momentum, you can get these 3 parameters. They are radius A0, right? A0 is about 0.53 Armstrong, right? Okay, I hope you still remember. You need to remember this very well. And energy is K. K is what? 13.6 electron volt, right? Okay, I hope you remember. And the velocity V0 when Z equal to 1 and Z equal to 1, sorry, and then R equal to 1. So V1 will be 1% of speed of light, right? Okay, so you need to remember these 3 parameters very well. And also we know that the radius is proportional to n is integer number power 2 and reciprocal to the Z. So if you increase the Z, and radius will decrease. When you increase the n, and radius will increase by power of 2, right? Okay, so once you have, if Z equal to 1, you have 0, A0, right? 1 here. So you have A0, n equal to 1, and n equal to 2 will be 4A0. N equal to 3 will be 9A0. N equal to 4 will be 16A0. Okay, so this is 1R, 4R, 9R, 16R. Okay, and also, and then the second one is energy is proportional to the minus Z power 2 divided by M power 2. Again, if we increase the Z, the energy will be increased. Well, regardless of this minus. Of course, if you think of this minus, D, increase Z, energy will decrease by power of 2, right? Okay, and then you increase the Z, N increase, the energy will decrease. So assume Z equal to 1, you will get what? Z equal to, N equal to 1, you will get minus K. And this is minus quarter K, minus 1/9 K. Okay, so this is the one here. And then velocity is proportional to the Z divided by N. Okay, so as I told you that if Z equal to 1, and then velocity 1 will be 1% speed of light, right? And then if N equal to 2, that will be half V1. If N equal to 3, that's 1/3 of V1. And if Z equal to 4, that will be quarter V1. Okay, and we also learn the energy diagram, right? Lowest and highest. The highest will be N equal to 0. Sorry, energy equal to 0. And we also learn the ionization energy. We have first ionization energy, second ionization energy, and third ionization energy, etc., etc. Okay, so this is Bohr atomic model. And last week we start to, so this Bohr atomic model is all developed by theoretically and hypothesis. And there's another group who are interested in experiment. They start with the spectrums, light spectrums of the atomic hydrogen. And we also learn this, right? I hope you still remember. We start with introduction of gas discharge tube. We put the hydrogen into the gas discharge tube. We got 4 discrete wavelengths. And they are red, green, blue, and purple. And they have their specific wavelengths. Okay? So, and J.J. Balmer delivered according to these wavelengths, he developed an equation. I hope you still remember. And we were thinking, can Balmer's equation validate with the Bohr model? Can this experiment match to the theoretical hypothesis or theoretical equation? Can we do that? So before we introduce that, we want to know the details about what's going on in gas discharge tube. And we start to introduce you matter energy interaction. I hope you still remember. Okay, so in this case, we realize that all the elements has their own fingerprint, which is spectrum. Okay, so hydrogen has his own spectrum. Oxygen has his own spectrum. So all the gases, if we put different gases into the gas discharge tube, you will get different color. And you can recognize this color by analysis is spectrum. And as a result, you will be able to know what kind of element is in the gas discharge tube. Okay, so this is spectrum for hydrogen, helium, lithium, oxygen, carbon, nitrogen, neon, etc. So you got different colors. You put this all together, you got this color. Sorry, you put all, for example, this is helium, right? You put all of this light, or we call electromagnetic wave, put it together, you got the color like this. This is the combination of this spectrum. Okay, and this is combination of this spectrum. So that we can understand, we can realize what kind of elements in a start, a specific start. We can identify the spectrum. Okay, and in the end, we introduce you cathode ray tube. This is a very old type television and monitor. When I was young, we used this, and now we don't use this. The principle of the gas discharge tube, cathode ray tube is the same as the principle of the gas discharge tube, except the cathode ray tube has phosphorus, okay, which the electron hit the phosphor. This is kind of material, and then the light will come out. There's 2 or 3 different lights, which are the red, green, and blue, and so that you can have full color on the screen. That's what the principle. But of course, nowadays you don't use this CRT. You use flat panel display, especially LCD, right? Liquid crystal display. And sooner or later, as I just told you last week, and light emitting diode, LED, will come out as a TV for your TV or screen. Okay. Okay. So when we talk about spectrum, actually there's a full scale of a spectrum. Not only what we can see, but also it extends to the short wavelengths and the very long wavelengths. And this is called electromagnetic spectrum. It will start from very long wavelengths and become very short wavelengths. For example, this is the wavelengths we can see from, this is the gas discharge tube. These 4 wavelengths we can see by our naked eye. They are red, green, blue, and purple. So this is in the range of the wavelengths in the range of 400 to 700. Okay, and then the reciprocal of the wavelength will be the wave frequency. Okay, so we need to follow these equations called Planck-Einstein relations. Okay, ladies and gentlemen, I want you to remember this equation. Okay, and this might be in your Kahoot next week or in your midterm exam. And this is not difficult at all. You know this, as you know, you probably learned this when you are in high school. So energy equal to h times v. H is Planck constant, right? V is the frequency, equal to h times c. C is the speed of velocity, divided by lambda. Lambda is the wavelength. So according to this equation, if the unit of the energy we use is electron volt, and lambda we use is nanometer, so we can change this equation to a very easy equation called E equal to 1240 divided by lambda. So you have the relationship with the lambda and the E. You know the Planck constant and speed of light is a constant, right? So you get this together and you put the dimension, the unit of the dimension of the energy and unit of dimension of the wavelength to become nanometer and the electron volt. You got this equation. And ladies and gentlemen, please remember this equation. That will be very easy for you to calculate. For example, if I want to tell you what's the energy of the blue light, you know the visible light we can see is between 400 to 700 nanometer. So if you put 400, this is blue light, right? And you have longer wavelength, that will be red light. So if you put 400 here, then you will be able to tell me what's the energy of the blue light roughly. Okay, so could you tell me what's the energy of blue light? You use the unit, you use the unit of the electron volt. Can you do that for me? 1240 divided by 400, that will be about 3.1 electron volt. And how about red light? That will be 1.8 electron volt. So this need to be in your mind. Okay, as a student in the material science, please remember these numbers. Okay, if I ask you what's the wavelength, what's the range of the wavelength in the visible light? 1.8 to 3.1. What's the wavelength of the visible light? 400 to 700. Okay. So obviously you understand this is a very small scale, very small range in terms of the electromagnetic spectrum. So you can have a very long wavelength that will be in we call the FM, AM or FM radio, okay, and then go to the microwave wavelength, and we go to infrared, and we go to visible, and energy getting stronger and stronger, right? So the wavelength of visible and infrared is about what? Size of the bacteria. You cannot see. You cannot see with your eyes, which is about less than 1 micrometer. Okay, so this is in the range of nanometer. Okay, so if the infrared energy gets stronger, ultraviolet, you know, you need to have umbrella under the or your sunglass under in a sunny day, because you don't want ultraviolet light to damage your eyes, right? Okay, and after ultraviolet light, that will be X-ray, including soft X-ray and hard X-ray. Of course, you don't like X-ray, right? You'll damage your health, your body. And obviously, if the wavelength get stronger, energy gets stronger and stronger, the wavelength gets shorter and shorter. So this one will be gamma ray. Gamma ray is very, very strong. And this X-ray will be in the size of atom. And this will be the size of the atomic nucleus. Wavelength is very, very small. Okay? So the important information in this slide will be this one. Please remember this one, these 4 numbers, and also this equation. Okay, so let's have a quick recall about energy conservation, which is transition energy. So again, you have a nucleus in the middle, in the center of the atom, and you have orbits. And let's say this is Ni, and I can be 1, 2, 3, 4, 5, 6, 7. It's an integer number. And then you have NF, N sub F, F stand for final, I stand for initial. Okay, F stand for final. So we, according to Bohr atomic model, we understand if the electrons stay in this stage, in this orbit, or this orbit, they all has their own energy, velocity, and radius, right? Okay, so we can calculate the energy easily by according to the Bohr atomic model. So, and this is the equation. I hope you already remember this very well. Okay, so assume we have one electron in the orbital of Ni, and then we give the energy, and this is target gas. We give energy to this element by free electron. For example, it can be alpha particle, whatever, right? Alpha particle, proton, whatever. And in this case, we have gas discharge tube, so we have free electrons. So if the free electron hit this target gas, if the energy is big enough, and then this energy will be about half of the mass times velocity power 2, right? Okay, this is kinetic energy. Of course, this has no potential energy. This element has no, this electron has no potential energy. Okay, and then because the energy of this electron is higher than the transition energy transition from this one to this one. So this is transition energy, okay? Transition energy. Between these two, of course, this electron will jump up to the orbit, which is farther than this Ni. So this is called excitation, right? And electron go down will be called relaxation. So this excitation come out, and we understand in order to transit this electron from here to here, it required energy. The energy required is, according to this Bohr atomic model, we understand the equation being, you can write the transition energy will become like this. No problem, right? Okay, and then we have a scattered electrons, which is from the primary electron. This is called primary electron. The primary electron becomes slower because energy is slow. Energy is transferred to this atom, right? So this is called scattered electron. And we understand the energy of electron will be like this. And speed is slower than this instant speed and the scatter speed. Okay, and then according to Coulombic attraction, this electron will drop and emit energies in the form of the electromagnetic wave. Or if we regard electromagnetic wave as a particle, we call it photon. Okay, and this energy will equal to what? The transition energy of this electron. So the energy of proton will equal to the energy of the electron, transition energy, transition energy of the electron, right? Okay. And this emitted photon will be like this. And we understand that the form of the energy in the form of the energy of the photon is this, right? Energy photon equal to hv, and we understand, we just introduced this to you. And so this one need to be equal to this one. Am I right? Okay, so instant energy, according to energy conservation, the instant energy, this one will equal to transition energy plus scatter energy. And transition energy will be also equal to the photon energy. No problem, right? Okay. So let's recall Bohr postulates for hydrogen models. There are 6. And now, in the previous slide, we use this Planck-Einstein relations applied to the electron energy. This is the postulate from Bohr, and we just derived that equation for you. Okay, so now let's think of how Bohr model will be validated for the Balmer model. Because Balmer model they got an equation experimentally, right? They did experiment and they got this model. And Bohr got a model by theoretical calculation. Okay, so according to the energy transition of electron, let's see will these two models match to each other. Experimental model and the theoretical model. So according to the postulate number 6 of the Bohr model, and this is delta E transition equal to photon, right? Okay. And this is initial, this is final. We just change it like this. And we understand this is the transition energy of the electron will be equal to the energy of the photon. Okay, this transition energy, and this is the photon energy. So let's rearrange this equation like this. Can you do that? Easy, right? Easy. So this is lambda. This is the reciprocal of lambda equal to this. And of course, we understand this is the frequency. So Bohr model can divide the equation like this. And because K, Hc are constants, so you can easily to calculate the K, H, and C as 1.1 times 10 to 7 meter minus 1 per meter, right? Okay, so are you with me so far? No problem, right? This is easy. Okay, so this is derived by Bohr atomic model. So let's assume if Z equal to 1, which is hydrogen, right? And then NF is 2, final is 2. Can you do that? Yes, we can, right? So let's assume something like this. The equation will become like this. 1.1 times 10 to 7th, and then this and this. And because n equal to 2, then energy transition has to, this n equal to 2, so that will be 3, 4, 5, 6. 3, 4, 5, 6. This is from Bohr atomic model. And then do you find out something interesting now? If you assume in the Bohr model Z equal to 1, NF equal to 2, then this equation is exactly the same as Balmer model. Balmer model, you know, in last week I told you that according to that 4 discrete wavelengths of the hydrogen, the bar find out this equation experimentally. But this is theoretically derived model. So and this is the same. You know, this is, you know, R is 1.1 times 10 to 7th. So that's why Bohr atomic model is very beautiful, because no matter how you want to challenge this model, it's inflexible. It's very strong. It stays there, inflexible, right? Okay, so however, in the previous slide, we told you that all the energy go to the orbital number 2. But however, this is not true, because you know for the energy transition, the energy can go to from number 5 to number 2, can go to number 5 to number 1. So there are many series after the development of Balmer series. Okay, so let's assume this is atom and n equal to 1, 2, 3, 4, and we understand for the atomic model, n equal to 1, energy will be minus 13.6 electron volt, right? N equal to 2 will be minus 3.4 electron volt. According to the equation, I'm sure you can do it very easily. N equal to 3, that will be 1.5 minus 1.5 electron volt. Okay, and n equal to 4, n equal to 5, like this. For the transition or the model, you can just easily calculate. For example, if I have transition from n equal to 2 to n equal to 1, you just get these two numbers together and divide it. You can get an answer. And we understand bar series, the model is like this. This n equal to 2. So everything go to number 2. This number 1 here, number 2 here. Energy level is minus 3.4 electron volt. So Balmer series is 3 to 2, 4 to 2 energy, okay? 3 to 2, 4, 3 to 2, 4 to 2, 5 to 2, 6 to 2, 7 to 2. Of course, you only can see these 4 wavelengths, not this one, because this is infrared. Sorry, this is not infrared, this is ultraviolet ray. Energy getting stronger. Okay, this and the final NF equal to 2. So this is we call medium energy. However, what happened to energy go to number 1 orbit? We call this Lyman series. Lyman series is n equal to 1. We call this high energy. Energy is larger than 3 electron volt. And the light we can get is ultraviolet. And the Paschen series is low energy, is infrared, because the energy all go to number 3. And this is number 4, Blanket series. Okay, so if you can get an equation for the Balmer series, can you get an equation of Paschen series? Can you get an equation of Lyman series? Yes, you can, because you just change this number here. So I'm sure at this moment you will think, well, Professor, can we get a general equation for all the series? Yes, you can. This is called Rydberg equation. Rydberg equation is the final initial like this. So this can be N2 will be Balmer, N1 will be Lyman, N3 will be Paschen. So why can we do it final here? So this is called Rydberg equation. I just want to tell you that this is not to scale. You know, this is not proportionally, the distance is not the same. Okay, so this is to scale. Lyman scale, you know, the energy is very strong, right? This is high energy. This is medium energy. This is a Balmer series from here. And this is Paschen series. And, you know, energy getting smaller and smaller. So this is Rydberg equation. Ladies and gentlemen, please remember Rydberg equation. Okay, I want you to remember, I will tell you. If you don't need to remember that, I will also say to you, you don't need to remember that. But this is don't you think this is a very beautiful equation? Yes, it is, right? It's very beautiful. Like E equal to mc squared, mc power 2, right? Right. So this is Rydberg. Rydberg, you know, the development of this is very quick. There are many brilliant scientists found these equations and matched to the Bohr atomic model. So in the very beginning, Armstrong, right? A. Armstrong, he found the light spectrum of hydrogen. And J.J. Balmer, he found the equation. And Rydberg, he derived this equation. Okay. Okay, it's for your information. So let me summarize the light spectrum of atoms. You know, all the elements has its own fingerprint, which is light spectrum. So spectrum is For the sunlight, it's continuous. We all understand this because there are many, many elements. So for the specific element or individual elements, you have discrete. It's not continuous, it's discrete light spectrum. For example, the gas, you can put anything to the gas discharge tube, you can get different spectrum. And we understand you need to remember Rydberg equation. Okay? And you also need to, in order to know Rydberg equation, you also need to know the matter-energy interactions and energy conservation. Right. So this is the spectrum of the hydrogen and the Bohr atomic model. Okay, so and before we move to the next topic, which is quantization of energy in electrons in the multi-electron atoms. So when we think of the electrons, Bohr atomic model, there are only one electrons, and this electron is quantized. But what happens if we have 2 or 3 electrons in the atoms? Will this electron quantized, or will this electron quantize and follow the atomic model? The answer is half is true, half is not true. That means that energy, the electrons, there are many electrons in the atoms and they are quantized. This is true, but they don't follow the rule of the atomic model, Bohr atomic model. And this is the story I'm going to tell you after the Kahoot. And now let's refresh ourselves and we play Kahoot in the atoms. So this is another experiment called Frank-Hertz experiment. Frank-Hertz experiment is that instead of putting the element hydrogen into this gas discharge tube, they think, wow, can I put different element into this gas discharge tube? So they put mercury into this mercury vapor in this gas discharge tube. As you can see, this is fluorescence light. We all have mercury in this light. Okay, and they put the mercury vapors into this gas discharge tube, and then the color come out in terms of white. The white color come out. Of course, you understand that according to matter-energy transition, you understand this is the spectrum. Okay, but in this case, you can analyze the spectrum, but they don't. They put the electron beam will shoot, right? Shoot a mercury vapor, and then mercury vapor, because of energy transition, the light will come out. So they collect the current here. The electrons being related to current. The current come out and they collect the current. Okay, they collect current. They also collect the electrons. So this is the layout, the schematics diagrams like this. Electron beam hit mercury, light come out, and they have a cathode. They have an anode here, and then they analyze the current. So this plot is that this is voltage, this is current. Voltage is the cathode voltage. That means if you have a strong voltage, that means the energy will be higher, right? The energy of the electron will be higher. Okay, and the current will be the collection, the numbers of the electrons. Okay, the numbers of electrons. Right, so this is the energy diagram of mercury, for example. Energy diagram of energy level of the mercury. For example, this is E low and E high. And we have a energy transition, right? So assume that the electron hit this mercury vapor atom. And if you remember, we talked about this last week. If the energy is not strong enough, there's nothing happen. The energy will go through without exchange energy, right? Okay, so again, let's increase the energy of the electron. That means what? If I increase the energy of the electron, that means what? I have to increase the voltage, right? And then because there's no interaction with the electron and the mercury, this electron energy will go through and we will collect the electron here. So the current will increase. Am I right? Okay. So pass through, there's no interaction. Okay, there's no interaction. So you'll get a little bit, see here? You know, I draw this very, very hard. I try to please you very, very well. So please, you need to please me very well in your midterm exam. Okay, you see that the current increase. If I voltage increase, the current increase because there's no interaction. And one more, if I increase the current energy, voltage increase, and this energy is not enough to have a excitation and radiation of the electrons. Again, the voltage increase, the current increase. Until what? Until the energy is reached to the threshold of this gap, right? If the energy is enough, increase to the length, if we can regard this, the length of this equal to this, what happened? There's no electron come out, or energy of electron will be very, very small. That means what? The current go to 0, right? Okay, and then you can see the light because photon come out. So as a matter of fact, the current dropped, and the and they measure the voltage is 4.9 volt for the mercury. It makes sense, right? It makes sense. However, they continue to do experiment. They increase the voltage. They increase the voltage, and what happened? The light come out, and also what? Slow electron come out. Right? So slow electron come out, that means what? The current increase. So, and this, we understand this is not ionization energy, because ionization energy, the first ionization energy is about 10 electron volt. And we only have 4.9 electron volt. It doesn't enough, energy is not enough to ionize the electron. So we understand this is the transition of the electron. Transition the energy of the electron to the photon electron, photon energy. Okay, so I increased energy again. Okay, I just told you that the photon energy is 4.9 electron volt, and we understand this. We measure the currents here. So if we increase make the energy increase, what happened? And we have slow electrons and current increase, right? Current increase, and you will come out from here. And funny thing is, if we increase, it will become like this. And now you understand this is what? 4.9 volt, and what is this? 4.9 volt. This is 4.9 volt. So what does this experiment tell you? There are more than 1 electrons, and all electrons are quantized. Okay? So can you explain this? Yes, you can. Why? Because once this electron goes through, and this electron got enough kinetic energy, and that will hit the second mercury atom. And second mercury atom will get the same result of this. And third one. Right? Okay, so this experiment tells you that electrons are quantized. The gas tube with a mercury vapor. I don't want to read all the sentence to you. Please read this by yourself. So the important thing is that at 9.2 volt, each electron has just enough energy to participate in elastical collision, excite 2 mercury atoms, and then be left with the no kinetic energy. So energy of mercury is quantized. So this is not only hydrogen in the electron in the hydrogen is quantized. Also, the electrons in mercury is quantized. So the important message here you need to digest is Bohr model does not apply to multi-electron atoms. Model doesn't apply, but the assumption of the energy quantization extends to the multi-electron atoms. Okay? Of course, they got Nobel Prize because of this experiment, and this is very important. You know, this quantum mechanics move forward, one step forward because of this. So similar pattern. So they might think, wow, if they put mercury, can I put another elements? Yes, you can, because the neon will be 19 volts. Okay? And neon got the red orange light. That's why you can see in the pub, right? When you want to have a drink. Right, so the quantum mechanics is very, very important. And 1 year ago, this Nobel Prize winner goes to quantum entanglement. Quantum entanglement is also it's very hard for you to imagine this. How come this kind of phenomena? But this is too far for us to understand. Okay, I don't have time to explain it to you. If you are interested, I just want to tell you that the quantum mechanics is very, very important now. You know, you need to study what is quantum computer, quantum computation. There are two. This is quantum. Okay. So the speed of a quantum computer is very, very fast compared to very, 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 very fast. Okay, compared to conventional computer. Right, but this is out of scope in our lecture. Anyway. Right, so now let's talk about limitation of Bohr atomic model. This is very important. Okay, this is Michelson-Morley experiment. So Michelson-Morley experiment is that they found something wrong with the Bohr atomic model because they found out if they do the experiment in detail, they found out this red line is not a red line. It's kind of red lights. There are two, actually. So you know that according to the model, Reiber's equation, this is from N3 to N2, right? Okay, but if we make a very good experiment, you will realize this one is thicker than this 3. And if you do it very carefully, you find out these are the combination of, this line is a combination of 2. So Michelson-Morley wonder what's going on, what happened. Please remember, this is also quantized. The energy also quantized. Okay, so Michelson-Morley, they found out that it's very, very close, doublet. So measure 2 lines, photon has unique value of the wavelengths, 2 different transitions, these 2. So if they need to think what's going on with this, because N3 to N2, there are 2 spectrums. That means what? That means there are 2 possibilities. The first possibility is this. Energy transition of electron is this. The second possibility, they might have 2 very, very close orbits. The second probability is this one go to this one. That's why they will have 2 lines. Or N2 has 2 orbits. This is also another possibility. So these 2 prediction will all apply to these 2 lines here. So what's going on? So scientists, they are sure there are 2 lines here. So this is one of the things cannot explain by Bohr atomic model. Of course, this Michelson is a very great scientist. Experiment, he can do very good experiments. He got Nobel Prize because he can measure the speed of the light by this interferometer. Very good, very excellent experiment. You can imagine how can you measure the things which is very, very fast, and he can. Very good. So he got Nobel Prize. And this is the first things against the Bohr atomic model. The second thing against the Bohr atomic model is called Zeeman effect. Zeeman effect is like this. Zeeman, he is a postdoc. Do you know why it's postdoc? You are bachelor now, right? If you graduate, you get bachelor degree. And if you study, you can go further to do your further study, you get master degree. Right? After master degree, you can get PhD degree. Okay, and what happened to a PhD? Okay, if you want to do further, you can do postdoc. But there is no degree for postdoc. You become a staff. You receive salaries. You receive money. Okay, and after postdoc, you can be a professor if you want to. This is like my track. I got master. I got PhD. I got PhD in England. I got postdoc in Japan, and I come back to Taiwan as a professor. Okay, so postdoc is that after you got PhD degree. And there's one day he want to do an experiment, but his professor, his supervisor, doesn't let him do this. He said, "No, don't do that. I don't know the reason. I haven't read this." And he want to do it, and he do it. He did, and he got fired. His professor said, "I asked you don't do that. Why you do this? If I fire you." So he did it. He was fired, and he got Nobel Prize because of this experiment. Is it amazing? Okay, what happened to him? He put a magnetic field, and he put the gas discharge tube between the magnetic field, or you can put the magnets. And then he found out something wrong, or something happening. Is that if there's no magnetic field applied in this gas discharge tube, the spectrum you got is normal. However, if you apply the magnetic field in this gas discharge tube, you found that the wavelength, the spectrum split. In Taiwan is 笔切, bit right? Split. It can split into 2, 5, 3, something like this. And you think, wow, what happened? If I apply magnetic field, why energy split? Energy become one. The wavelength is represent energy. Energy can have one energy become two energies. It doesn't make sense, right? If you think of the Bohr atomic model, it doesn't make sense. And funny thing is, or I shouldn't say funny thing. Most important thing is, if we increase the magnetic field, the intensity. If we increase the magnetic field, the degree of splitting will be wider. B not equal to 0. This splitting will be wider. And this cannot explain. Bohr atomic model cannot explain this. So if there's one wavelength, why light split it? Why energy can be split it? If you go to physics department, you can see this kind of experiment. You can see this kind of instrument. It's called Zeeman effect apparatus. Okay, so this is the gas discharge tube, and you put a magnetic field here, apply magnetic field here. So if you have a 0 Tesla, the Tesla is the unit of the magnetic field, 0, and mercury waveline will be like this. If you apply this, you see that it becomes blue and split, energy split it. They got Nobel Prize because of this. Okay, this is Zeeman. Okay, another thing is Stark effect. So Stark think that if the magnetic field can split the spectrum, can I use electrical field to split the electrons? The answer is yes. He got Nobel Prize. Okay, if you are in that era, if you are in that era and you in the top of the scientist research, and it will be easier for you to get Nobel Prize, right? If you go to the right professor who can fire you, right? Or you got the right professor who can help you, okay? And it's not difficult to think in that way, but anyway, not only this, but also you need to work hard for this, right? So more again, the stock give a stock apply the electrical field, and then the spectrum split it. So Zeeman effect and Stark effect is all like this. So this Bohr atomic model cannot explain this. These are all for curiosity from in the science. They're curious why this happened, and I want to prove Bohr's atomic model is right. But in the end, this kind of curiosity can become a very useful tools for our daily life, for our use in our daily life. This is the start of the MMR, magnetic resonance imaging. This is very important nowadays. MRI is very important. If you go to the hospital, you can find your tumor in your body using this. So there are three limitations for the Bohr atomic model so far. They are Michael Maury experiment, Zeeman effect, and Stark effect. And this is MRI, okay? And of course, they got Nobel Prize. You know that in the beginning of this century. Right. So I'm sorry because I have a very important meeting at 10 o'clock. So I need to leave before 10 o'clock. So and also this shell model is a very important model. I don't want to stop in the middle. So I think I will leave this knowledge. I want to introduce this to you next week. On Friday, we don't have lecture. Right? Am I right? We don't have lecture, right? Or do you want to have a lecture? No, I don't want. I don't want either. Okay? Good. So I think let's talk about this next week. I'm telling you stories, right? There are many stories to get together and make things interesting to you. Right. So I hope you enjoy the lecture today.